The next presentation here in this session is about wideband antenna design and integration challenges for 5G devices. And our speaker is Petri Mustonen from Radientum OI. And what I can see here from his bio, he's holding several patents in this area. And please, now you can start with your contribution.
Okay, so thank you very much for the introduction. So let's get into it. So at first, a few words about who we are. So the company is Radientum, and it was founded 5 years ago by Nokia Microsoft engineers. And we help companies of all sizes to develop antenna solutions for wireless products in various industries. About 60% of our revenue comes from the international markets. And we have a mission to bring optimal wireless performance to your device. The typical antennas we are working with are PCB trace antennas, flexible PCBs, SMDs, LDS, and also external antenna components. And we are working with various industries like consumer electronics, automotive, IoT, logistics, healthcare, wearables, telecommunications, RFID, a smart home. So pretty much everything. And within these 5 years, we have worked over 120 customers and over 250 antenna projects. And our customers comes from over 25 different countries worldwide. And we are located in Finland, in Tampere. So first a little bit background about this presentation. So I'm going to show you some examples about issues that might come during antenna integration and design. For that, we created a simple PCB. It was manufactured and simulated and measured. The PCB size is 140 millimeters by 50 millimeters. And for this, we use Ethertronics chip antenna. We got the simulation model from the antenna from Ethertronics, but it's kind of a protected model, so we don't actually see how the antenna is done, but we can just use it for the simulations. And we made it like a custom PCB to our measurements, and it was pretty much copied from the reference board of that Ethertronics antenna. Just few modifications, like holes for the screws and so on. And the antenna we use here, it covers frequencies between 700 megahertz to 3.8 gigahertz. So it's a 5G Sub-6 GHz antenna. So I'm gonna show some effects that comes from battery and wirings with the plastic chassis, and then PCB on top of PCB structures, so this kind of backpack PCB, and then a few examples about different use environments, and then also the effect of the external wires, like a charging cable, for example. So here we have the first pictures about the PCB. It's on the left side. On top is our custom-made PCB, and below that is the Ethertronics reference board. The size in this picture is a little bit different, but actually they're identical. So only difference here was that it has the holes for the screws and also for the pin headers we are going to use later on. And the simulation models can be also seen there, but as it's protected, we don't see anything except the shape of the PCB and then the antenna. So first we measured our custom PCB and the reference PCB just to make sure that everything was okay in our antenna layout. And from the measurement results, we can see that both curves, the measured curves are pretty much the same. So no major differences there. So the antenna was okay. And then also there's the simulation results shown there. And the simulation follows the measurements quite nicely. The efficiency is a little bit more optimistic with that simulation results, but that is pretty expected. So first we add that top PCB. So we have a smaller PCB on top of that main PCB, and we connect them together by using pin headers. So the distance between those PCBs is about 2.5 millimeters. And we have a few cases where the PCB is grounded on different locations. Like in the picture in the left, PCB1 case, we have 2 pin headers on the left corners of the PCB. And then in PCB2, we have groundings on the top side. And then at the PCB3, we have groundings on the right side. And from the results, there's the simulated and measured results. We can see that, for example, in the PCB1 case, so the blue one, there is quite a big notch in the efficiency, just above 1600 megahertz. The same is also with the simulated ones, which are the dashed curves, but the effect in the simulation is not that big as it in the measurements. But then the PCB2 case, there's some ripple in the efficiency, but nothing major there. But then in the PCB3, so the green curve there, we can see that there is actually now notch around 1800 megahertz, which actually now hits in the middle of the bands. So the PCB1 case, it's not a problem because it doesn't hit any important frequencies, but now in this case, the PCB3 is now making the efficiency worse there. And here we have a few more cases. So the PCB4 is now grounded on the bottom side, and then the PCB5, which is grounded on all of the corners, and case also where the PCB is left floating. And from the results, we can see that the case with the 4-corner grounding and the floating case, the results are pretty much identical. So in this case, it doesn't matter if it's grounded or not. But then again, at the PCB4, we can see some ripple at the efficiency around 1600, but it's also out of the band. So based on these measurements and also simulations, we can see that the 4-corner grounding is actually the best case, because then the results are more stable there. The floating would be also okay, but I guess in most of cases, that is something that cannot be done, because usually you need some kind of traces going from PCB to the other one. Then we forget that top PCB and we add a battery and a wire. So we have 2 cases here. The battery, it's modeled in simulation just with like a metal block, and it has short wires. And on the left picture, there's wires are connected to the main PCB about in the middle of the PCB. But then there's another case where the battery is rotated, so the wires are now on the end of the PCB. And from the results, again, we can see that in the low bands and also in the highest band, so about 3 gigahertz, there isn't any difference between these cases. But then again, here in the mid bands, we can see that, for example, in the 1900 area, there is the notch in the efficiency, which was also there just with the antenna itself and the PCB only. But now that notch is a little bit deeper due to the antenna mismatch, or it's detuning a little bit there. But then also in the green case, so when the battery is rotated, both simulation and the measurements, we can see that in around 2.6 gigahertz, there's a notch in the efficiency. So again, between these 2 cases, then the case where the battery is not rotated then would be a little bit better. Some more testing with the wires. Now we have a longer wire. There's a battery wire 1, and then the battery wire 2. And the wire 2 is much longer than the 1. And from the results, we can see that now this wire 1 case, there is again this kind of notch in the efficiency just in the middle of the low band. But then again, that battery wire 2 case, there isn't anything, so the low band looks good. And at the higher frequency, the high bands, there isn't any difference between the cases again. But then in the mid band area, we can see that there is notches there. The one deeper one is with the battery one, and then the battery wires 2 case had only like smaller notches there, but multiple of them. So not that big difference there, but again, if some of these should be chosen, then I guess then the battery wires 1 and 2 would be better because it doesn't affect the low bands at all. And the third case with the more wiring, now we add that top PCB back there. 2 cases, the top PCB is grounded and floating, and now the wires from the battery are split, so the wires go to the main PCB but also to the top PCB. And here we can see that there is quite a big effect there on the low band, very big notch in both of the cases, and in mid band there's also a very similar result in both of the cases, small notches there caused by these wires. So based on that low band region there, this kind of, for example, structure wiring wouldn't be that good. So the better case then would be then to have the short wires to the main PCB and then just use those pin headers, for example, to get the voltage to the top PCB. Okay, now we forget again the battery, and we use the plastic covers here. So we have the PCB only case, and then we have the PCB with the plastic covers. These covers were just off-the-shelf components found it from DigiKey. Just happened to be the right side for our PCB, so we use this one. It's the ABS plastics. And from the results, we can see that on low band, again, there is a bit detuning of the antenna, so the frequencies will shift more to the lower frequencies. The only difference effect here is maybe the highest frequency of the low band. There you can actually see that the efficiency drops about 1.5 dB due to the mismatch or detuning. And then in the higher mid bands, we can see that with the covers, the efficiency drops more above 2 GHz, and that is mostly due to the detuning of the antenna also. So the matching is getting a little bit worse there. And again, at the high bands, there isn't much difference here. The PCB is a little bit separated from the top and bottom part of the chassis because there's that kind of like screw towers. So the antenna is only touching the plastic just at the end of it. So on top and at the bottom, there is plenty of like air before that plastic itself. So that explains a little bit why it doesn't detune more than this. And then we move to the use environment cases. Now we have the full device here simulated. So it has the covers and the top PCB and also the battery. And it's simulated on free space, and then also simulated when it's put on top of like a wooden plate and also on top of metal plate. This was to simulate the effect what would happen, for example, if the device would be mounted on a wall. So at the results again, we can see that the wood wall case, the low band, the antenna is again detuned. Now already quite a lot here at the higher frequencies. And then in the mid-band region, we can see that the efficiency drops quite a lot. It's partly due to the dielectric losses of the wood, but also the detuning effect of the antenna. And same also goes to the highest frequencies. But then in the metal plate case, we can see that at the low band, there isn't that kind of like frequency shift. but there is like a very big gap in the efficiency. So there is actually a resonance coming here from the metal plate that will eat up this efficiency here quite a lot. And on the mid band and in the high band, there isn't that big difference there. So the antenna is not that much like detuned, but it's just more like the currents in that metal plate will then cancel the radiation up here around the 700 megahertz, which will affect quite a lot to the efficiency. And this is something that you cannot fix with antenna tuning itself. So probably the only way to get rid of this kind of effect, then it would be to increase the distance from that device to the metal plate. And still few use environment cases. So in the first one, the device is taken on hand. And then the other one, which is a bit more rare, but you can see it sometimes, is that the device is potted with some kind of silicon gel material. So in like some use cases, when the device is used in like an explosive environment, there's a requirement that all the electronics have to be covered with some kind of potting material to get rid of any sparks there. And of course, that's bad for the antenna because the gel material will go all around the antenna, touching it basically. And from the results in hand case, again, we can see the detuning at the low band, not surprised there. And also in the mid band, not that much detuning anymore, but it's again just an efficiency drop, mostly due to the dielectric losses of the hand. And the same one goes also to the highest frequencies there. But then in the potting case, the red one, we can now see a very heavy detuning effect here at the low band. So, and also here in the mid band region, and all of these, we can see all of these frequencies are clearly shifted more to the lower frequencies. And this is already that big detuning effect that's also something you cannot compensate just with tuning component changes there. And the last test here was that the external cables. So we add a 50 centimeter long wire, just going from 3 different directions from the device. The wire 1 case, we have the wire going straight to the down, and then in wire 2 case, it goes straight to the right, about at the middle of the PCB, and a wire 3, it goes straight to the right, the top part of the PCB, so very close to the antenna. And the results show here again efficiency notches at the low band, now in wire 1 and wire 3 case, but actually the wire 2 case, there isn't any effect there. Then in the mid band, there is a lot of notches again in all of these cases. So and then in the highest frequencies, there isn't again any effect there. So again, based on these cases, maybe if the low band would be optimized, then that wire should be inserted from the middle of the PCB. Then quick summary. So during the antenna design phase, the whole mechanics have to be taken into account. So every part that is added to the design may have an effect to the antenna, even if it's placed far away from the antenna or close to the antenna. And all the groundings have to be considered very carefully. And also the use environment have to be taken into account. The device can be optimized in certain use case, like on wall, on hand, or in pocket, for example. And for this kind of use, the EM simulators are very useful, or even must tools, because they help to get the effect of all of these, like in very early age of the device manufacturing or the project. So actually, even without any prototype is manufactured, this problem can be seen already. Thanks for Etetronics for providing us the simulation model from the antenna. And most of all, of course, thank you all the watchers there. That was all.